So we're going to get started with inverse trig functions. This is the last type of function that you need to be able to take the derivative of. And it's everyone's least favorite kind of function. I'm going to spend some time going over trig in general, the reason for an inverse trig function a little bit. In this course, it's a non-calculator course, so you are going to be expected to evaluate inverse trig functions with the exact value without using a calculator. And I wanted to kind of discuss that in great detail. This is something that you're going to do now, obviously. It's also an embedded skill for Unit 2 as well. So this is important. I certainly don't want you to just say, oh, I don't know inverse trig, I'll be okay. It's going to hit you here, and it's going to hit you in Unit 2. So let's just get it over with. Okay, let's get back into trig functions in general, right? So I think I'm going to break this up into 2 videos. Okay, I'll go over some of the pre-calculus prerequisite material with inverse trig functions in general, and then in the second video I'll do the more calculus-based derivative process. So you know from your previous math classes that if you have a right triangle, here's our angle down here with theta. This is the side opposite, this is the side adjacent, and the hypotenuse is always the leg opposite the 90-degree angle. So this is your right triangle trig. Maybe your earlier teacher used the mnemonic SOHCAHTOA to remember your relationships with sine, cosine, and tangent. That sine is opposite over hypotenuse, cosine is adjacent over hypotenuse, and tangent is opposite over adjacent. The other 3 trig functions are just reciprocals. Cosecant is the reciprocal of sine, secant is the reciprocal of cosine, and cotangent is the reciprocal of tangent. So you do need to know those basic trig functions for sure. And what I'm going to try to do here is talk about the graphs of the original trig function, sine, cosine, and tangent, and then develop the inverse trig function itself. I think that's necessary to understand how to evaluate these things, which again is your responsibility. So if you know how to evaluate arc cosine of 1, that's great. If you're not sure, listen up. And your textbook does go over a couple of these ideas as well. You could use Khan Academy to supplement this if it's been a while since you've been in a traditional pre-calculus class. So I could start with any of the trig functions. I'm going to start with cosine. So this is your cosine graph. This is what you probably sketched in a pre-calculus class. You probably sketched some trig functions. You talked about amplitude and period. You can kind of see here in red, the period of the cosine wave goes from 0 to 2 pi. Right? A period is how long the cycle is before it starts to repeat itself over and over and over again. So this is the traditional cosine wave. It's an even function if I think about some old characteristics of that particular function. But for the purpose of what we're doing here, I do want you to realize this is a continuous function. There are no gaps, breaks, or holes. For every angle, there is a cosine value. The highest value is 1, the smallest value is -1, and it takes on every value in between. When it comes for an inverse function, to find an inverse function, in order for the inverse to be a function, the original graph you're taking it from, meaning the cosine, has to be considered 1-to-1. And let me be clear, I feel like this is the weirdest vocab word ever, right? So here's 1-to-1. Okay, what 1-to-1 means is it has to either be, I'll just draw an arrow here, it's a graph that's either always increasing from left to right, or it's always decreasing. Focus here on always. And if you look at this cosine wave from left to right, it's decreasing, and then it increases, and then it decreases. This is a problem. This graph is not 1-to-1. Therefore, the entire cosine wave does not have an inverse function. It fails the 1-to-1 condition. However, we can have an inverse function as long as we do something crafty like restrict the domain. That means I'm literally going to take most of the function off and ignore it. What the general practice is I will pick a piece of this graph that is one-to-one, that is either always increasing or always decreasing. I want to pick a section that has all of the outputs from +1 to -1 without repeating anything. And so the standard practice is to use this section right here from 0 to pi. Okay, so I'm just going to kind of draw in here. Here is us looking at the restricted cosine wave. That, we have a biggest value of 1, a smallest value of -1. We're going to go all the way from 0 to pi. And I'm going to put pi over 2 there in the middle. And we're only looking at this little part of that cosine wiggle. So if I just pay attention to that one little part, that one little part is always decreasing. You can say that that thing is 1-to-1. Now, because I've restricted the domain, my domain is not all real numbers anymore, like it is for the regular cosine wave. We've cut off most of the graph. The domain for this is just 0 to pi. We've really restricted the possible angles we're able to graph. But my range goes from -1 to 1. I got all of those outputs included in this one little measly section. Okay, now what I'm going to do on this other grid is I am going to graph the inverse cosine function, which you can use the notation arc cosine. That's what I prefer. You will see some textbooks, your own textbook and others, use the inverse notation. See that little -1 there? That does not mean reciprocal. That means the inverse of the cosine function. Now, what I need you to know about a function and its inverse is that really they just switch domain and range. They literally switch x and y coordinates. So let's take a coordinate here. On the cosine wave, the restricted cosine wave that we were talking about earlier. As an ordered pair, this is x equals pi and y equals -1. That's a point on that curve. Well, all I'm going to do is I'm going to switch the ordered pair to make the inverse function. I am instead going to plot -1 comma pi. Here's -1 comma pi. Here is pi over 2 comma 0. So I am going to graph 0 pi over 2. And this is 0 radians 1 as my y value. So I am going to plot 1, 0 radians. This is the graph of the arc cosine wave. I don't necessarily need you to know what it looks like. I just need you to know that it's static. It is not continuous. It does not go on and on forever. It's continuous, but it doesn't go on and on forever. And what I want to also mention here is that the domain and range of an inverse function just switch. So the domain, the inputs of arc cosine are -1 to 1. And the range, that means your answers are now the domain of the original 0 to pi. This is important to know. When you're evaluating an inverse trig function, your answers are angles. Okay, so that is a really, really important thing to realize. Okay, so when I ask you to evaluate an inverse trig function, your answers are angles. And I'm going to try to write it as such. Okay, so let's be clear about what we're going to do. We're going to evaluate some things. I'm just going to make some stuff up, and we're going to translate it. So I'm going to ask you to evaluate arc cosine of -1. Okay. What this means, and I can write it this way. I can say, look, what this means is the cosine of some angle is -1. Your answer is what angle has a cosine of -1. Your answer is what is that angle? And let's be clear. Your answer is, hey, what is my angle answer that fits in the range from 0 to pi? So here's how I look at this. I think of the unit circle, because I learned the unit circle. I look at the top half of the unit circle and I say, look, let me make that look better. I say to myself, look, here are my range of allowable answers, angles, from 0 to pi. This is where pi over 2 is. You have some other cute angles in here. That's pi over 3. This is pi over 4. This is pi over 6. 2 pi over 3, 3 pi over 4, 5 pi over 6. So I need to find where the cosine value, or the x-coordinate on the unit circle, is -1, and that is happening right here at pi. So my answer for the arc cosine of -1 is pi. Okay. So you can kind of see that from our graph. If I input -1, my answer, which is that angle, is pi. Okay. So I'm going to do another one. Arc cosine of 1/2. Again, I'm going to translate what that means in terms of trig. What it means is the cosine of some angle is 1/2. And you have to answer an angle. Your answer is an angle. And your answer has to be between 0 and pi. So you're looking on the unit circle where you have an x-coordinate of 1/2. And that's actually here. There's the ordered pair on the unit circle for pi over 3. At pi over 3, the x-coordinate is 1/2. That is the cosine value. So I'm going to go ahead and answer the arc cosine of 1/2 is pi over 3. Okay. I'll do another one. How about something, okay, arc, oops, I don't know what's going on there. Arc cosine -√2 over 2. Okay, these are all like special angles that you learned in pre-calculus. I learned the unit circle. You might just recognize these ratios and have them memorized. That's another strategy that some pre-calculus teachers use. But when you see something being phrased of, hey, evaluate this inverse trig function, arc cosine of -√2 over 2, this, what I wrote in gray here, is what it means. It means the cosine of some angle. And by the way, your answer is the angle between 0 and pi, only that range, where the cosine value happens to be -√2 over 2. Now, the cosine happens to be the x-coordinate on the unit circle, which means you should be looking over here in quadrant 2. That's where you have negative x-coordinates. And the moment where you're looking for, where the x-coordinate is -√2 over 2, is right here at 3 pi over 4. Here's the ordered pair from the unit circle at 3 pi over 4. So my answer here would be 3 pi over 4, because that is an angle, because your answer is always an angle, and it's between 0 and pi. Okay, so you might need to practice evaluating inverse trig functions. It's an important skill. You will have to do it in this class, and so you might need to brush up on that a little bit. Okay, but again, all of these inverse trig functions, everything I'm saying is going to be used not only here, but in the next unit as well. So that's why I wanted to really focus on it. If you're just coming off of, fresh off pre-cal and calc 1, you may not need as great of detail. Okay, I'm going to move on to the next trig function, which is sine, and we're going to get to inverse sine, arc sine, and I'm going to do the same thing. Once again, this is a similar wave to the cosine wave. It is continuous for all real numbers. The domain of the sine function is all real numbers, for sure. But once again, this is not considered one-to-one. We need to restrict this function to get a good little piece of it, so that it takes on every output value from -1 to +1. And we generally just use a standard little piece of it. We use this piece here. Here I'm going from an output of -1 all the way to +1. And so I'm going to draw that on the grid here. So this is going to be our restricted sine wave, where we're saying, look, I have an ordered pair of pi over 2 comma 1 at this location. It goes through the origin. And then over here, this is negative pi over 2 comma negative 1. So this is what you would consider an odd function. It goes to the origin. It has origin symmetry. This is the only piece of the sine wave that we can really discuss as having an inverse function. Because this piece is always increasing. That's great. Then it has the potential to have an inverse function. The whole point to an inverse is that you just switch the x and y coordinate. So these ordered pairs that I've drawn in here, all I'm going to do to get the inverse function is I'm going to switch the x and the y. Okay, so this restricted domain, I just want to be clear, the normal sine wave has a domain of all real numbers. This one goes from negative pi over 2 to positive pi over 2. We are really lopping off most of the graph and saying we're only going to focus on that little range on the x-axis, that window on the x-axis. Your range is still negative 1 to 1. You wanted to make sure you picked a section that has all the outputs from negative 1 to positive 1. Sine ratios cannot be more than 1 or less than negative 1. Okay, so I am going to graph the arc sine function, which obviously is the same thing as sine to the negative 1. I generally use arc sine, but you'll see me use sine to the negative 1 from time to time. So I will graph this. Now, again, what's happening here is I'm going to reverse the x and the y axes. So instead of having negative pi over 2 and pi over 2 on the x-axis, those become values on the y-axis. And same thing with the 1 and negative 1. Those used to be on the y-axis. They're now on the x. I'm literally switching x and y. And I'm going to plot these ordered pairs. So I'm going to plot this guy down here. Normally this is pi over 2, 1. I'm going to plot 1 pi over 2. It goes through the origin, and I'm going to give it the right shape. This is the graph of arc sine. I don't necessarily need you to know what that graph looks like, but we will be talking about the mechanics of evaluating this. So the domain of the arc sine function, the inputs are negative 1 to 1. Inputs meaning the x values, okay? And your range are your outputs. Those are your y values. So see, once again, your answer to an arc sine function is the angle that satisfies the condition. Okay, so we're going to evaluate some of these. And so I'll do the same thing I did before. We'll just do some evaluations with arc sine. Okay, so let's try to evaluate, right? We're going to evaluate arc sine of 1. Okay, arc sine of 1. So what that means, I'm going to do the same thing I did before. It means the sine of some angle is 1. Your answer to an inverse trig is an angle. And it's an angle between negative pi over 2 and pi over 2 in this case. We're not doing 0 to pi like arc cosine. It's a different window of angles that you're choosing between. So going back again to the unit circle, what that means for me is instead of looking at the top half of the unit circle, I look at the right half, where this is pi over 2 that you're used to. Here are your special angles. There's 0, of course. Here's your negative angles. We kind of just label these in the negative direction. And that makes this negative pi over 2. That's the way I look at it. Now, the sine ratio is the y coordinate from the unit circle. So the angle that has a y value of 1 is pi over 2. And these are things you have to know and be able to do in this class. Okay. Evaluating another arc sine of negative 1/2. So again, that means a y value of negative 1/2. Well, where the y values are negative are down here in quadrant 4. And right here at negative pi over 6, this ordered pair is root 3 over 2, comma, negative 1/2. So that means my answer to arc sine of negative 1/2 is negative pi over 6. Okay. If you need to write that translation in there, go ahead and do it. But hopefully when you get fast enough with it, you won't need to do that. But that is what that means. Arc sine of negative 1/2 means, hey, there is an angle, so that the sine of that angle is negative 1/2. Find it. And make sure your answer is between negative pi over 2 and positive pi over 2. That's the only values you can use for your answer. Okay. If I do one more of these arc sines, we can do arc sine of root 3 over 2. That's another common one. Okay, so it's positive, so I should be looking in quadrant 1. And I'm looking for a y coordinate of root 3 over 2, and that's going to be right here at pi over 3. That has a y value of root 3 over 2, and the angle is your answer. So your answer is pi over 3. Okay? All right. Moving on to tangent. The reason I put these on the same page is they have the same window of restriction. Once again, the tangent function has a problem. It has to always be increasing or decreasing. It also, I guess this function is kind of always increasing, but there's also something known as the horizontal line test. It has to pass the horizontal line test, meaning if you draw a horizontal line in, it can only cross at most once, and this crosses many, many times. So that is my problem here with the tangent function. Okay, what I'm going to do instead is I'm going to restrict the domain, as has been decided from a lot of other people. We're going to choose this little section of the tangent wave. It obviously keeps going on and on and on forever. But we are going to take that tangent wave and ignore most of it and only focus on that one little wiggle in between those vertical asymptotes. And those vertical asymptotes are at pi over 2 and negative pi over 2. The restriction is similar for sine and tangent. That's why I have them on the same page. Okay, so we will graph the arc tangent function over here just by switcherooing the x and y coordinate. Okay, so essentially what I'm going to do on this graph is I'm going to say, look, we had vertical asymptotes at negative pi over 2 and positive pi over 2 for the tangent function. That means they're going to translate to horizontal asymptotes if I switch them around, right? If these are x equals equations for those vertical lines, they switch to be y equals equations. And again, you don't necessarily have to know what the shape of it is. I'm just drawing it just to kind of, again, push the issue of domain and range. We are restricting the domain on the original tangent graph. The domain that we're restricting to, notice it's exclusive of these boundaries because you have vertical asymptotes there. Your range is all real numbers. See, there is no restriction on the outputs there. Okay, now that means for your arc tangent graph, your inverse tangent graph, those things reverse. Your domain is now all real numbers. You can plug in anything you want to on the x-axis. But your outputs are bounded between negative pi over 2 and positive pi over 2. So when you think about evaluating an arctan, it's the same idea as arc sine. I think about the unit circle. I think about the right-hand side of that unit circle. And what I do is I just put like open circles here to remind myself, like, hey, you're not actually going to answer pi over 2 or negative pi over 2 because those are not allowable values. But you're going to think about it the same way. And so I'm going to evaluate some arctan things in here for you. So arctan of 1. I'm going to translate that again. What that means is the tangent of some angle is 1. Tangent is y divided by x on the unit circle. And so I'm looking for where you divide y over x are the same x and y coordinate and they're both positive. And that's going to happen right here in the middle of quadrant 1. That's at pi over 4 because your ordered pair is root 2 over 2 comma root 2 over 2. So my answer to the arctan of 1 is pi over 4. If you change the inside to be negative, what ends up happening is it's basically the same location, but in quadrant 2. It's going to be down, I'm sorry, quadrant 4, excuse me. And we call that negative pi over 4. Okay? Because the ordered pair here at negative pi over 4 is, well, it's positive root 2 over 2, but your output, your y value, is negative root 2 over 2. And so if you do y divided by x here, you get negative 1. Okay? So you have to get familiar with evaluating some inverse trig. Those are the most important ones. All right. Now, I also want you to deal with converting from trig to algebra. This is also a very important skill that you will use later in this course for sure. And it comes up now. I might as well mention it. Okay. We're going to use this figure to rewrite or to write expressions in algebraic form for tangent of theta. So here's my picture, and I'll just switch colors. Here's your angle. Tangent, remember, is opposite over adjacent. So if I want an algebraic expression for the tangent of this angle, all I have to say is that the tangent of theta is x over 1. You could just say tangent of theta is x. That's it. You're just going to your right triangle trig and figuring it out. You're using those skills. Remember that cosine is adjacent over hypotenuse. So not as easy on this one, right? Because I know the adjacent side is 1. I don't have an expression for the hypotenuse. I have to find it. Okay, this is not sufficient. I can't just say 1 over the hypotenuse. I have to go find it. And you know, you can do this. This is the hypotenuse. This is the algebraic expression you're looking for. And you've got 2 of the sides labeled, so you can do it. You know the Pythagorean theorem says, look, if you've got a right triangle, leg squared plus leg squared equals hypotenuse squared. I'm going to use that. We're going to use Pythagorean theorem a lot in this class. 1 squared is 1. X squared is x squared, and this equals the hypotenuse squared. Now, I want to get this thing to say hypotenuse equals, which means I have to take the square root of both sides. Now, algebra says I should have a plus or a minus. This is a freestanding triangle, so I'm going to choose the positive value here. Okay, so that's the hypotenuse. It's the square root of 1 plus x squared. That means I can now go back and say what the cosine of theta is. It's 1 over the square root of 1 plus x squared. There it is. No need to rationalize that expression, by the way, guys. Okay, this you do not have to rationalize variable expressions in the denominator, so don't feel the need to do anything more with this. This is proper form. Okay. Now, I would suggest you pause the video and see if you can figure out some of these. If not, keep listening. And we're going to handle a variation of this. Okay, so this all might be fresh to you if you remember pre-calculus really well. You had a really good instructor and all of that stuff. I'm going to kind of do the same thing with sort of reorganizing this. So this was just kind of looking at a picture and, like, I don't know, thinking about a nice conversion for what tangent could be equal to algebraically, or cosine, or I could have done sine, or any of them. I just picked those 2. Here I have a different style of question, right? But similar skills needed for this. Okay, so I want to write this expression in algebraic form. Now, this is kind of weird, right? I'm not quite sure what to do with the sign on the outside. I'm going to get in there and I'm going to figure it out. What I'm going to do is pay attention to the inside here. I'll go with blue. I'm going to pay attention to this. What I'm going to do is I'm going to draw the picture that would actually look like this. So when we were evaluating the inverse trig, I kind of always rewrote what it meant. What does arc cosine of 1 mean, right? What does arc cosine of 3 over x mean? Well, what it means is the cosine of some angle is 3 over x. That's what we said back when we were evaluating the inverse trig. I'm doing that here. The cosine of theta is 3 over x. Draw a triangle where that is true. Here's theta. Draw a triangle so that the adjacent side is 3 and the hypotenuse is x. You did it, right? And that's pretty much what this picture was in the last example, right? we had the picture and we wrote what the tangent was. The tangent was x over 1. But you could go backwards. Well, if the tangent of theta is x over 1, draw a triangle where theta is here and opposite is x and adjacent is 1. So I'm just kind of going in this opposite direction from statement to picture instead of picture to statement. Okay? So back here. Arc cosine of 3 over x. I rewrote what that was. I considered it cosine of theta equals 3 over x. I drew my picture. This is great. All I need to know, I don't actually need to know what theta is. Like, there's no way for me to figure it out. I have no idea what theta is. But look, all I have to do is come up with the sine of that angle. So what do I need to answer this question? To answer this question, I need opposite over hypotenuse. What do I know right now? I know that the hypotenuse is is x. Okay. Okay. So all I have to do is figure out that opposite side, which I'll label in here. That's what I'm looking for. And you have the skills to do it. You have 2 out of 3 sides, right? Pythagorean theorem. So remember, Pythagorean theorem says leg squared plus leg squared equals hypotenuse squared. You're solving for the opposite side, right? So that means I'm going to bring that 3 squared over. Remember, 3 squared is 9. I'm going to take the square root of both sides, and when you do that, you get plus or minus. But again, this is a freestanding triangle, so we're going to select the positive length. We're going to say the opposite side is the expression, the square root of x squared minus 9. Now that doesn't simplify at all. You're stuck with it. So I think instead of writing opposite here, let's write the square root of x squared minus 9. That was the only thing missing to my answer, right? I drew this picture in blue. I'm now supposed to answer what the sine is. Well, sine is opposite over hypotenuse. I now know that opposite is the square root of x squared minus 9. This is the answer to this question. It asked for an expression, an algebraic form. What is equivalent to the sine of arc cosine of 3 over x? It's the square root of x squared minus 9, all divided by x. Okay. These are important skills, this idea of substituting and rewriting. This is not something that you're only going to see now. Again, you're going to see it in Unit 2. That's why I'm going slow and making sure that I explain all of this, because in Unit 2, I'm just going to do it. Okay. Here we are in example 3. Again, pause the video, try it on your own, and then restart it. Okay. I'm going to do the same thing. I'm going to write the expression in algebraic form. I'm going to do it in the same way. Maybe I'll just use different colors just because. So can I go with this? I don't know. No. Yeah, that's fine. So in here, I'm going to draw a picture of what that means. Remember, that means the sine of some angle is 2x. I'm going to put over 1 because I want to see a ratio in there, right? I'm going to draw a freestanding triangle. I'm going to put theta wherever I feel like it. Opposite hypotenuse. So I've got a great picture. What I need to figure out is what the cosine of this thing is, right? I'm trying to figure out the cosine of this angle. I want the cosine of that angle. Now I know the cosine is adjacent over hypotenuse. So what does that mean for me? Well, I know the hypotenuse is 1, so mission accomplished. What I don't know is what the expression would be for the adjacent side. You know Pythagorean theorem, you know how to handle this. You know one leg squared plus the other leg squared equals the hypotenuse squared. Now, I'm solving for the adjacent side, so 1 squared is 1. Please be careful over here. 2 quantity squared is 4x squared. And again, I'm going to take the square root and I'm going to jump the gun here. We're only going to choose the positive value because we're talking about a freestanding triangle and I want to select a positive distance here. That is my adjacent side. Okay, so instead of writing adjacent, I can say, nope, I figured it out. It's 1 minus 4x squared. So I can come back over here and say, nope, I figured it out. The adjacent length, I've got it worked out. That is the answer to your question. the cosine of arcsine of 2x is equivalent in algebra to that rational expression. And certainly you wouldn't have to write the over one, right? But this would be acceptable.